Okay, thanks for the presentation. Thanks also to all the organizers for giving me the opportunity to give this talk. For real, it's very nice to me to be here. I'm very happy to be here and can present you my work title, The Reduction of Time-Dependent Hamiltonian System from an EPO point of view, in collaboration with David Iglesias, Juan Carlos Marrero, and the Patron. So, first of all, the following example of a time-dependent Hamiltonian system motivates our new approach to the reduction of these systems. So, we consider an n-dimensional harmonic oscillator seen by an observer that moves with a constant velocity. That is, if we study a classical particle of mass m moving in a harmonic oscillator potential with frequency omega in n dimensions, the potential is centered at the origin, and now we suppose that the system is observed from an inertial frame moving at a constant velocity, which, without loss of generality, we can assume that takes this form. So, under this assumption, the configuration bundle is given by the projection onto the time of the configuration space, and the phase space of momentum is given by this product space. So in this example, the Hamiltonian of the system is given by this equation, which is just the kinetic energy plus the potential energy. You can see that the potential is central, and his time dependence is due to the velocity of the observer. Moreover, we have this Lie group action of the real line on the configuration space given by this expression. So here you can see that the action shifts the time in such a way that the Hamiltonian is preserved. That has a consequence. We have that the projection onto the time doesn't preserve the action. This means that this diagram is not commutative. So this fact implies that we cannot apply the standard Albert reduction for the symplectic manifold, because for that we need this diagram to be commutative, and it's not. So this problem was studied by Gutierrez, Agredos, and collaborators, where here collaborators mean my supervisors and David. So they introduced the reduction of mechanical presymplectic structure to overcome these limitations. So here, just to mention, when I say mechanical presymplectic structure, I mean just a closed and degenerate form of Courant 1 whose kernel is generated by a global vector field. So here, I would like to emphasize a standard construction for obtain a mechanical presymplectic manifold from a Hamiltonian system in the cotangent bundle. So we have the cotangent bundle, a Hamiltonian function on it. So we take a regular value of the Hamiltonian. So with this, we have that the level set of that regular value will be a mechanical presymplectic manifold with the mechanical presymplectic structure given by the pullback of the canonical symplectic structure by the canonical inclusion, whose kernel is generated by this vector field, which is just the restriction to the level set of the Hamiltonian vector field. So here I would like you to remember this construction for the end of the talk. So you have just to remember this at least. So take this in your mind. So then our goal will be to use these ideas to describe the reduction of time-dependent Hamiltonian system using discrete formalisms, and this will involve reduction of presymplectic structure of Courant 2 and reduction of mechanical presymplectic structure. So don't confuse, when I say mechanical, it doesn't mean that this is of Courant 1. But in particular, we will see that the trajectories of the reduced time-dependent mechanical Hamiltonian system will be transformed into the geodesic of a metric on the reduced space, which is a quite surprising result. So, sorry about the spoiler, so you have to pay attention for it to the end of the talk also. So, then let me present you the main ingredients that we need. We consider a connected manifold of dimension n+1 fiber over the real line by a vibration which is not necessarily canonically trivializable. Thus, maybe to understand it better, let me write in the blackboard the trivial case. So in the trivial case, we have that our manifold will be the product space of an n-dimensional manifold with the real line, fiber over the real line, and with these coordinates. So that's what we have in the trivial case. So now we consider the dual space of the vertical bundle, where the vertical bundle is just this set of tangent vectors satisfying this condition. So here we have the phase space of momentum given by this space with these coordinates, and here just the projection. Okay. So now it's well known that the cotangent bundle is a principal R bundle over the dual space of the vertical bundle, where the dual map of this inclusion is the principal R bundle with the associated principal action given by this expression. So here you can see the black window. Okay. So here in the trivial case we have the extended phase space of momentums given by this space with these coordinates.
Try a different pen, Carla.
Oh.
Try a different pen. It's hard to read.
Okay. That's why I ask.
Let's see.
Yeah, better. Okay, maybe. Oh no, it's better. Sorry. This I can. Can you see this one? Maybe. Okay. Yeah. This. Okay. Now here the canonical projection, and here our principal bundle. Okay. Now it's clear, no? Thanks. So in the next step we consider a Hamiltonian section of this principal bundle, which will induce a homogeneous extended Hamiltonian function in the cotangent bundle, which is characterized by this equation. So here, how it's going the things here. If we consider Hamiltonian section here, will be given in coordinates by this condition. We take a Hamiltonian section, so it takes values in the dual space of the vertical bundle. So the first coordinates are the same, and the last one will depend on a function in the dual space of the vertical bundle, and it will induce a extended Hamiltonian function in the cotangent bundle, which is given in coordinates by this expression. Okay, so that's what we have in the trivial case. Now in the next step, we consider a Lie group action in our manifold and the corresponding cotangent leaf in the cotangent bundle. So now it's natural condition to impose that these two actions, the principal action and the cotangent leaf in the cotangent bundle, commute. So to guarantee that these two actions commute, the necessary and sufficient condition is that this one form needs to be G-invariant under the action. So then, from now on, we will assume that this condition holds. So we have that these two actions commute, and then also, thanks to this assumption, we have that the tangent leaf restricts to the vertical bundle. So taking the dual of that restriction, we can obtain a Lie group action in the dual space of the vertical bundle. Also, the non-preservation of the time of the projection depends on a multiplicative function in the Lie group satisfying this equation, which means that the theorem presented at the beginning needs not hold, has we want. So also from this multiplicative function, we define this one cocycle in the dual space of the Lie algebra in this way. To continue, we also need to assume that the Hamiltonian section is the equivariant, which means this equality holds where here we have the action in the cotangent bundle, and here the action in the dual space of the vertical bundle. As a result of this assumption, we have that this extended Hamiltonian function is G-invariant, which means this equality holds. Okay, So, as anticipated at the beginning, to solve the limitation of Albert reduction, we need to introduce presymplectic manifolds. So now I'm going to present you the two essential structures that we will use. So first, it is well known that the cotangent bundle is a symplectic manifold with the canonical symplectic structure. However, it's also a presymplectic manifold of Courant 2 if we endowed it with this presymplectic structure, which is given by the canonical symplectic structure and depends also in the standard Hamiltonian function, and it is a closed and degenerate form of Courant 2 whose kernel is generated by these two vector fields, which this R is the infinitesimal generator of the principal action, and this is the vector field of the Hamiltonian vector field of the standard Hamiltonian function. On the other hand, we have that the dual space of the vertical bundle is a presymplectic manifold of Courant 1. It means a mechanical presymplectic manifold if we endowed it with this structure, which is given by the pullback of the structure that we have in the cotangent bundle by the Hamiltonian section. And it is a closed and degenerate form of Courant 1 whose kernel is generated by this vector field, which is just a projection by the principal bundle of the Hamiltonian vector field in the cotangent bundle. And it is the time-dependent Hamiltonian dynamics. So from now on, this first stage will be always referred to the theory of presymplectic theory of Courant 2, and this second stage will be always referred to the presymplectic theory of Courant 1. Now we have that both of these spaces are endowed with momentum maps, which are the first integral of the system. So in the first case, we have these momentum maps, which, as you can see, depends on the standard Hamiltonian function and on the one cocycle, which is characterized by this formula. And this momentum map in the cotangent bundle induces another momentum map in the dual space of the vertical bundle, which is characterized by this equation and this one. So as you can see, both of them are characterized by the infinitesimal generators of the correspondent actions. Now we need to assume one technical condition, which is that this happens, which means the kernel of the structure, the intersection of the kernel with the tangent space of the orbit needs to be 0. It's a technical condition, but we will need it later, so I will write it in the blackboard. If I can, of course. Maybe I think you can see it. So we will assume this. With this assumption, we have that these both momentum maps are submersions, so that's what we need. Then with this, we have that our original Hamiltonian system restricts properly to the corresponding level set of a certain regular value, mu, in the dual space of the Lie algebra. So it means that all the maps and vector fields involved restrict properly to the corresponding level sets. So here now, under certain regularity condition, we are in a position to apply the reduction theory at each stage. So for this, we use the reduction of presymplectic manifolds theory developed by Echeverría Enrique and collaborators in 1999. So with this, we obtain that the Gaussian space of the level set over the isotropy subgroup will be a reduced presymplectic manifold in the first stage, and also a reduced presymplectic manifold in the second stage, with the corresponding reduced map, the reduced structure, and the reduced dynamics. So, but we can ask a question: is this structure are also in the first stage of the same Courant? I mean, this structure will be of Courant 2 and this of Courant 1. So the answer is yes, and we have it because of, if you remember, we have here the principal bundle with the principal action, and here the infinitesimal generator of the action, which restrict here. So with this, we obtain that the reduced map of the principal bundle will be again a principal bundle with a reduced principal action, and here the infinitesimal generator of this principal action. So with this, we have that the kernel of this structure will be is given by this this infinitesimal generator and this vector field, which is the projection of this one by this map. So also here in the second stage we have that the kernel of this reduced structure is given by this vector field, which is the projection of the vector field we have here. So what we have obtained? We have obtained that our original system has been reduced to another to a reduced system in which we have the same the same thing we have in the original system. We have in the reduced system. So we have obtained here a reduced presymplectic manifold of Courant 2 again, and here a reduced presymplectic manifold of Courant 1. So that's all the theory I wanted to tell you. But just to conclude, maybe if I have time, I want to show you an example that illustrates this theory. So we want to consider a Hamiltonian, which is a time-dependent mechanical Hamiltonian system, which will be given by a kinetic energy plus a potential. So today, yeah, and one thing I forgot, it was like this. The condition I wrote you in the blackboard before was also to guarantee that the Courant here is preserved. That's why I wrote this condition there. Sorry, I had forgot it. It was important. So yeah. So going again to the example, we consider a mechanical Hamiltonian system. So to obtain this, we need to consider a metric in the vertical bundle, a invariant metric, which is not an usual metric. Then we, with this metric, we can obtain this kinetic energy in the dual space of the vertical bundle, and we consider also the invariant potential. So with this, the Hamiltonian function will be given by the kinetic energy plus the potential. And now the next goal is to obtain a reduced potential in the cotangent bundle of the quotient of the manifold with the group. So to do this, we need to obtain a reduced metric in this quotient space, which we can do it with some technical things, but we can obtain a reduced metric. With this again, we obtain a reduced kinetic energy in this quotient space, and as the potential was invariant, we can obtain a reduced potential in the quotient space. So again, with all these ingredients, we have that the reduced Hamiltonian will be given by the reduced kinetic energy plus the reduced potential. Next, assuming that the cocycle is non-zero, we can take an element such that when we evaluate it in the cocycle is 1. With this, we can prove that the momentum map in the dual space of the vertical bundle is given by this formula, which is not very important, but I can show you that it depends on the one cocycle, this new element, and the Hamiltonian function. If now, as an example, we obtain a regular value, which is a multiple of the cocycle, which is lambda times the cocycle, as it is a multiple of the cocycle, we have that its isotropic subgroup will be the whole group. So now, with these ingredients, we conclude that we prove that our reduced mechanical presymplectic manifold here will be isomorphic to the level set of the reduced Hamiltonian function of this value lambda, where the reduced presymplectic mechanical presymplectic structure will be given by the canonical symplectic structure in this quotient space. So here, we have this symplectic manifold, the cotangent bundle of the quotient space. We had obtained the reduced Hamiltonian function, and we obtain these isomorphisms, which in particular the dynamics is given by the reduced dynamics is given by the restriction to the level set of the Hamiltonian vector field of the reduced function. So, what I asked you at the beginning, I wanted you to remember one construction. So if you remember it would. This construction coincides with the standard construction to obtain a mechanical presymplectic manifold that I presented at the beginning. So in particular, here we have that our manifold, in our case, is the quotient space, and our reduced manifold, and our reduced Hamiltonian, sorry, is the Hamiltonian we take here. So it's exactly what we have obtained. But in this case, we have that the dynamics is the reduced dynamic is given by the restriction of the geodesic flow of the reduced metric minus this term, which is the vertical lift of this one form. But I also told you that our reduced dynamics will be transformed into the geodesic flow of a subtrain metric. So we have this term which we don't want it. So what metric is this? It's just the Jacobi metric, which is given by this expression. It depends on the value lambda and on the reduced potential. So with this, we obtain that our reduced dynamics will be the geodesic flow of the Jacobi metric, which is a quite surprising result. So that's all I wanted to tell you. Just mention maybe some present work, which is like we would like to develop in this example for another regular value such that the satisfying this condition, which is the isotropic subgroup, coincides with the whole group. And maybe you have noticed that the structure that we have, in the, this doesn't write, but the structure that we have, the structure that we have in the dual space of the vertical bundle depends on the choice of the Hamiltonian section. So we would like to provide an intrinsic structure on it that is independent of that choice, and then to develop the reduction process in the presence of a symmetry D group. So that's all I wanted to tell you. So thanks for all attention.
Let's ask questions. The dual of the vertical bundle,
Yeah.
that inherits a canonical Poisson structure from the quotient of the cotangent. So you can see that so the cotangent of the Q is a symplectic manifold, and it projects on, like, you have an action there. It does not quotient the symplectic structure, but it does quotient out the Poisson structure, and then in the dual of the vertical bundle you have like a canonical Poisson structure.
Yeah.
Have you analyzed it from this point of view? Like how this interplays with this Poisson structure?
No, we haven't think about it. Maybe it would be very nice to see from that point of view, but I wouldn't do it.
Okay. Thanks for the talk.
Thanks for the question.
Very
Great.
good.
We can talk about that in the social dinner.
Any other questions?
What do you gain using this reduction scheme instead of going to the reduction theory of Dirac manifolds? I mean, do you recover all of these results if you apply the reduction theory for Dirac manifolds?
I don't know much about the Dirac, so I don't know.
Thank you for the talk.
I have a question slightly apart from the objective of the talk. You said in this fibration that this fibration of Q over the timeline, it's not necessarily trivial.
Yeah.
Do you have in mind some example of system in which this projection is not trivial?
In this, we are trying to. This, for example, in this case, we have here. It's general. It's not necessarily trivial. In an example.
If I may intervene.
Yeah.
Generally, the point is that it may be a trivial bundle, but cannot be trivialized in a canonical.
Yeah, exactly.
In a canonical way, if I understood correctly.
Yeah.
No questions? Let's thank Carla again.